Hello students. In today's video, we'll study about mechanical properties of fluids which are given in chapter number 10 of physics for class 11. This is part 1 of our video lecture on this topic. In this chapter, we shall study some common physical properties of liquids and gases. Liquids and gases can flow and are therefore called fluids. It is the property that distinguishes liquids and gases from solids in a basic way. Fluids are everywhere around us. Earth has an envelope of air and 2/3 of its surface is covered with water. Water is not only necessary for our existence, every mammalian body constitutes mostly of water. All the processes occurring in living beings, including plants, are mediated by fluids. Thus, understanding the behavior and properties of fluids is important. Unlike a solid, a fluid has no definite shape of its own. Solids and liquids have a fixed volume, whereas a gas fills the entire volume of its container. We have learned in previous chapters that the volume of solids can be changed by applying stress. The volume of solid, liquid or gas depends on the stress or pressure acting on it. When we talk about fixed volume of solid or liquid, we mean its volume under atmospheric pressure. The difference between gases and solids or liquid is that is the difference between solids or liquids is that the solids or liquids, the change in volume due to change of external pressure is small. That is, the change in volume is small. In other words, solids and liquids have much lower compressibility as compared to the gases. Shear stress can change the shape of a solid, keeping its volume fixed. The key property of fluid is that they offer very little resistance to shear stress. Their shape changes by application of very small shear stress. The shearing stress of fluid is about million times smaller than that of solids. In this session, we will study about pressure, density, Pascal's law, hydraulic machines, Archimedes principle, and stream flow. Please listen to the lecture very attentively and note down important points. I welcome you once again. Having introduced the topic of today's lecture, that is mechanical properties of fluids, we will proceed further to define a quantity called pressure. Pressure is defined as a perpendicular force per unit area, or it is also expressed as the stress at a point within the confined fluid. Please see the figure above A, which shows the forces exerted by a fluid. When an object is submerged in a fluid at rest, the fluid exerts a force on its surface. This force is always normal to the object's surface. This is so because there were a component of forces parallel to the surface. That is, the object will also exert a force on the fluid parallel to it as a consequence of Newton's third law. This force will cause the fluid to flow parallel to the surface. Since the fluid is at rest, this cannot happen. Hence, the force exerted by fluid at rest has to be perpendicular to the surface in contact with it. This is shown in figure A above. The normal force exerted by the fluid at a point may be measured. An idealized form of one such pressure measuring device is shown on the figure on the right hand side. That is figure B, which shows the device for measuring the pressure. This consists of an evacuated chamber. This is an evacuated chamber with a spring. This spring is calibrated to measure the force acting on the force. That is, if we apply a force F on the piston, this spring shows the force acting on this piston. This device is placed at a point inside the fluid. This whole device, this whole device is placed inside a fluid. This is the fluid area accommodating the piston and the spring. The inward force exerted by the fluid on the piston, that is fluid exerts pressure on the piston, is balanced by the upward spring force. That the spring supplies the upward force and is thereby measured. That is the basic principle of the device. If F is the magnitude of this normal force acting on area A, this is acting area A, then average pressure is given by P average is equal to F by A by definition. P average is force per unit area. That is normal force acting per unit area. In principle, the piston area can be made very small. The pressure is then defined as a limiting sense. That is, pressure P is equal to limit of delta A, that is the small area tending to 0 F by A. That is P is equal to limit of delta A tending to 0 of F by A. Let it be equation 2. Pressure is a scalar quantity. Its dimensions are m into L to the power of minus 1 into T to the power of minus 2. The SI unit of pressure is newtons per meter square. It is also named as Pascal. The common unit of pressure is atmosphere, and that is the pressure exerted by atmosphere at sea level, which is expressed as ATM. 1 ATM is equal to 1.013 into 10 to the power of 5 pascals. Another quantity which is used to describe fluids is density, and it is represented by the Greek letter rho and written as rho as shown on the screen. For a fluid of mass m occupying a volume V, rho is given by the relation rho is equal to mass over V, where m is the mass and V is the volume and rho is the density. The dimensions of density are ml to the power of minus 3 and its SI unit is kg per meter cube. It is a positive scalar quantity. A liquid is largely incompressible, that is, we cannot compress it, and its density is therefore nearly constant at all pressures. Please underline, it is largely incompressible and its density is therefore nearly constant at all pressures. Whereas the gases exhibit a large variation in density with pressure. That means as we increase the pressure, the density changes, and we reduce the pressure, the density decreases. The density of water, that is the standard, at 4 degrees centigrade, that is 277 degrees Kelvin, is 1.0 into 10 to the power of 3 kg per meter cube. The relative density of a substance is the ratio of its density to density of water at 4 degrees centigrade. On many occasions, we compare the density of a substance with respect to density of water at 4 degrees centigrade. Hence, the relative density is a dimensionless positive scalar quantity. For example, the relative density of aluminium is 2.7. Its density is 2.7 into 10 to the power of 3 kgs per meter cube. Now, having defined density and relative density, we will compare the densities of some common fluids which are shown in the table on your right hand side on the screen. See, fluids are given in column number 1. Fluids like water, seawater, mercury, ethyl alcohol, whole blood, air, oxygen, hydrogen, and interstellar space are given on the first column. Fluid, this is fluid or gases. Fluid, gases also are included, liquid as well as gases. On the right hand side, that is second column, the density rho in kgs per meter given is shown, and its values you can note down, pause this video and note down one by one, and you compare. For example, the density of whole blood is 1.06 into 10 to the power of 3 kg per meter cube, whereas the other elements are also, fluids are also shown in the table. Pascal's law. The French scientist Blaise Pascal observed that the pressure in a fluid at rest is same at all points. This can be demonstrated by immersing a small element, trapezoid, right angle trapezoid A, B, C, D, E, F, which is immersed in a static fluid in a container. The forces FA, FB and FC are normal forces acting on surfaces. BEFC, ADFC and ADEB, which are AA, AB and AC respectively, which are denoted by AA, AB and AC respectively. The inclined component FB can be split into two components, horizontal and vertical, as FB sin theta and FB cos theta. Theta is the angle between the vertical element and the inclined force FB, as shown in the right hand side diagram. The fluid exerts pressures PA, PB and PC on the element, corresponding to normal forces FA, FB and FC respectively, as shown in the figure. Then, by equilibrium of forces, horizontal force FC is equal to FB sin theta, and similarly the vertical component FB cos theta is equal to FA. And by geometry, AB sin theta is equal to AC and AB cos theta is equal to AA by geometry. Let these be two equations 1 and 2. Dividing one by another, FB by AB sin theta gets cancelled. Therefore, FB by AB is equal to FC by AC. Similarly, here also FB by AB is equal to FA by AA. Hence, FB by AB is equal to FC by AC, that is equal to FA by AA. Therefore, PB is equal to PC is equal to PA. Hence, the pressure exerted is same in all directions in a fluid at rest. Now consider an element in the form of a horizontal bar of uniform cross section. The bar is in equilibrium. The horizontal forces exerted at its two ends must be balanced, or the pressure at the two ends should be equal. This proves that for a liquid in equilibrium, the pressure is same at all points in a horizontal plane. Suppose the pressure were not equal in different parts of the fluid, then there would be a flow, as the fluid will have some net force acting on it. Hence, in the absence of flow, the pressure in the fluid must be same everywhere in a horizontal plane. Let us state Pascal's law once again. The pressure in a fluid at rest is same at all points which are at the same height. A change in pressure applied to an enclosed fluid is transmitted undiminished to every point of fluid and the walls of the container. Variation of pressure with depth. The pressure of fluid varies with depth h according to the expression P is equal to Pa plus rho gh, where Pa is the atmospheric pressure, rho is the density of the fluid, and g is the acceleration due to gravity, and h is the height. This pressure P is equal to Pa plus rho gh is also known as absolute pressure. Now consider a fluid at rest in a container as shown in the figure. In this figure, point 1 is at a height h above the point 2. This is point 2 and this is point 1, and the height is h. The pressures at point 1 and point 2 are P1 and P2 respectively. Consider a cylindrical element of fluid having an area of base A and height h. As the fluid is at rest, the resultant forces should be zero, and the resultant vertical forces should balance the weight of the element. The forces acting in the vertical directions are due to fluid pressure at the top, that is P1A at the top acting downwards, and P2 into A acting upwards. Thus, if mg is the weight of the fluid in the cylinder, then P2 minus P1 into A should be equals to mg, or simplifying we get P2 minus P1 is equal to rho into GH. Atmospheric pressure. The pressure exerted by atmosphere is called atmospheric pressure. A common unit of atmospheric pressure is ATM. That is the pressure exerted by atmosphere at sea level, whose value is 1 atm is equal to 1.013 into 10 to the power of 5 pascals. That is equal to 1.01 bar, or it is also expressed as 760 torr. At the same level, the pressure will be same at all points. Otherwise, the fluid cannot be at rest due to pressure difference. Now we will define the gauge pressure. The difference between hydrostatic pressure and atmospheric pressure is called the gauge pressure. In this equation, we have seen P2 minus P1 is equal to rho GH. Therefore, the pressure depends on the depth of the point H the density of the liquid rho and acceleration due to gravity g. It does not, the gauge pressure does not depend on the amount of liquid, shape of the container or cross-section area considered. So, if a given liquid is filled with in a vessel of different shapes to the same height, the pressure at the base in each vessel will be same, though the volume or the weight of the liquid in different vessels will be different. This is the example of paradox. And the figure 2 at the bottom illustrates the hydrostatic paradox. The three vessels A, B and C contain different amounts of liquids, all up to the same height. Now we will take up worked example. Example number 1. The two thigh bones, femurs, each of cross-sectional area 10 centimeters square, support the upper part of human body of a mass 40 kgs. Estimate the average pressure sustained by the femurs. Assume the acceleration due to gravity g is equal to 10 meters per second square. Let us solve it. The total cross-section area of femurs is given by A is equal to 2 into 10 centimeters square. That is, the area is given. That is equal to 20 into 10 to the power of minus 4 meters square. This 2 is due to the two thigh bones. This 2 is for represent two thigh bones. That is, each femur has a cross-section area of 10 centimeter. Therefore, area is 10 into 10 to the power of minus 4 meter square. So, we have converted centimeter square into meters per square. The force acting on them is F is equal to 40 kgs. That is also given. That is equal to, in terms of Newton, that is equal to multiplying force into G, that is M into A, that is equal to 400 newtons. 40 into 10 is, that is in converted in newtons. Therefore, the force acting vertically down and hence normally on the femur. Thus, the average pressure is given by the relationship average pressure is equal to force per unit area. That is, P average is equal to F by A. Here F is 400, A is 20 into 10 to the power of minus 4. Substituting, we get average pressure as 2 into 10 to the power of 5 newtons per meter square. That is the answer. Now we will take up the next question. What is the pressure on the swimmer 10 meters below the surface of a lake? Here H is given as 10 meters and rho is the density of water. We are taking as 1000 kgs per meter cube. Therefore, taking the value of G as 10 meters per second square, assuming we know that P is equal to PA plus rho GH. That is, the pressure is equal to atmospheric pressure plus rho GH. Substituting the values, we get P is equal to 1 point atmospheric pressure value is 1.01 into 10 to the power of 5. That is atmospheric pressure plus 1000 kg per meter cube. That is the value of rho into 10 to the power of 10 meters per second square is the value of G, and height is 10 meters. I will read once again. The atmospheric pressure is the first term on the right hand side, and the rho value of rho is 1000 kgs per meter cube, and height is 10 meters per second square. Simplifying, we get the value of P as pressure as 2.01 into 10 to the power of 5 pascals. Please work out yourself all calculation in detail. This is about 100% increase in pressure from the surface level. At a depth of 1 kilometer, the increase in pressure is about 100 atm. Submarines are designed to withstand such enormous pressures. Measurement of pressure. Italian scientist Evangelista Torricelli, who lived from 1608 to 1647, devised for the first time a method for measuring the atmosphere. He used a long glass tube closed at one end and filled with mercury, which was inverted into a trough of mercury as shown in the figure on the right hand side. This device is known as the mercury barometer. So, atmospheric pressure is measured by a mercury barometer. The space above the mercury column in the tube contains only mercury vapor whose pressure is so small that it may be neglected. That is, the mercury column here inside the tube is very small and its pressure is also very small and its pressure can be neglected. Thus, the pressure at point A here at the bow A is P is equal to 0. The pressure inside the column at point B must be same as the pressure at point C here, that is outside the tube, that is in the trough, which is the atmospheric pressure. This is the atmospheric pressure, which is given by the relation PA equals rho GH, where PA is the atmospheric pressure, rho is the density of mercury, G is the acceleration due to gravity, and H is the height. See, the distance between A and B is the height H. It is found that the mercury column has a height, this H is equal to 76 centimeter at sea level. That is equal to 1 atmosphere, which is also written as 1 atm. The value of height can also be obtained using the value of rho of the liquid, that is the density of the mercury in this particular case. A common way of stating pressure is in terms of centimeter or millimeters of mercury. That is, mercury formula of mercury is Hg. A pressure equivalent of 1 mm is called a torr. 1 torr is equal to 133 Pascal units. The mm of mercury or torr are used specifically in medicine and physiology, whereas in meteorology the unit is bar or millibar. 1 bar is equal to 10 to the power of 5 pascals. The second method of measurement of pressure is open tube manometer. The figure of open tube manometer is shown on the screen. A open tube manometer is used for measuring the pressure difference. The instrument open type manometer consists of a U-tube containing a suitable liquid fluid. The suitable liquid like oil is used for measuring small pressure differences, whereas a high density liquid such as mercury is used for measuring the large pressure differences. One end of the tube is open here. The end here at one end is open and the other end is connected to a system whose pressure is to be measured. That is, we are required to measure the pressure P at the end A. The arrangement is shown in the figure. The pressure P at A is equal to, at this point A is equal to the pressure at point B in the tube. That is, A pressure at A is equal to the pressure at B. What we normally measure is the gauge pressure, which is P minus PA equals rho GH and is proportional to the manometer height. H, that as shown in the diagram, is the height of the gauge pressure. The pressure is same at the same level on both sides of the U-tube containing a fluid. For liquids, the density varies very little over wide ranges in pressure and temperature. We can treat it safely as a constant for our present purposes. That is, the density is treated as constant in case of all liquids. Gases exhibit large variations. Liquids exhibit very small variations in density due to pressure and temperature, whereas gases exhibit large variations of densities with changes in pressure and temperature. Unlike gases, liquids are therefore largely treated as incompressible. Question number 3. The density of the atmosphere at sea level is 1.29 kgs per meter cube. Assume that it does not change with the altitude. Then calculate how high would the atmosphere extend. Assume atmospheric pressure as the value of atmospheric pressure equals 1.01 into 10 to the power of 5 pascals. Answer. Now first we will note down the given quantities. It is given rho is equal to 1.29 kg per meter cube and acceleration due to gravity g is equal to 9.8 meters per second square. So using the relationship, atmospheric pressure Pa is equal to rho gh is approximately equal to rho gh. Substituting Pa is equal to atmospheric pressure is 1.01 into 10 to the power of 5 pascals. That is equal to rho is the value of rho is 1.29 and the value of G is 9.8 into H. We are required to calculate H in meters. Substituting the values and simplifying, we get height as 7989 meters. That is approximately equal to 8 kilometers. We have to note certain important points in this example. In reality, the density of air decreases with height. So, does the value of G. The atmospheric cover extends with the decreasing pressure over 100 kilometers. We should also note that the sea level atmospheric pressure is not always 760 millimeters of mercury as explained earlier. A drop in mercury level by 10 millimeter or more is a sign of an approaching storm. Question number 4. At a depth of 1000 meters in an ocean, what is the absolute pressure? What is the gauge pressure? Part C. Find the force acting on the window area of 20 cm by 20 cm of a submarine at a depth the interior of which is maintained at sea level atmospheric pressure. The density of seawater is 1.03 into 10 to the power of 3 kg per meter cube and the value of G as 10 meters per second square. Here the depth is given as 1000 meters, that is 1 kilometer, and the area of window of a submarine is 20 centimeter by 20 centimeter, and the pressure inside the submarine is at sea level is atmospheric pressure. Let us solve it. Answer. It is given height is equal to 1000 meters and rho is equal to 1.03 into 10 to the power of 3 kg per meter cube. We know that the absolute pressure P is given by PA. PA is here atmospheric pressure plus rho GH. Rho is the density, G is the acceleration due to gravity, and H is the height. So substituting the given values, we get PA as 1.01 into 10 to the power of 5 pascals. This is Pascal. Plus 1.03 into 10 to the power of 3 kg per meter cube into 10 meters per second square into 1000. Height is 1000 meters. So we get this value simplifying as 104.01 into 10 to the power of 5 pascals. That is absolute pressure is 104.01 into 104.01 into 10 to the power of 5 pascals. That can also be written as 104 atm in terms of atmospheres. So here from this previous step to this step we have converted pascals into atmosphere. Now second part is we have to calculate the gauge pressure. Let the gauge pressure be represented by the letter Pg. Pg we know it is the absolute pressure minus atmospheric pressure, that is P minus Pa is equal to rho Gh. Substituting the values we get 1.03 into 10 to the power of 3 into 10 meters into 1000 meters. Therefore that is equal to 103 into 10 to the power of 5 pascals. Therefore that is equal to 103 atmospheres. Third part, it is given the pressure outside the submarine is absolute pressure is equal to atmospheric pressure plus rho Gh, and the pressure inside is atmospheric pressure. Hence the net pressure acting on the window is the gauge pressure. Therefore Pg is equal to rho Gh. Since the area of window is A, 0.04 meter square, the force is F is equal to Pg into A. Putting the values, we get F is equal to 103 into 10 to the power of 5 pascals into 0.04 meter square. That is equal to 4.12 into 10 to the power of 5 newtons. Hydraulic machines. Hydraulic machines work on the principle of Pascal's law, which states that when an external pressure is applied on any part of the fluid in a vessel, it is equally transmitted in all the directions as shown in the figure. In the figure, a plunger pushes the fluid and creates a pressure, and this pressure created by the plunger or the piston is transmitted equally to all the three bodies C, A, B of different shapes. A hydraulic lift also works based on the Pascal law, and it is used to lift heavy loads. Similarly, hydraulic brakes also work on the Pascal's law principles. In these devices, fluids are used for transmitting the pressure as shown in figure 1. A hydraulic lift shown in the figure 2 has two pistons which are separated by the space filled with a liquid. So the two pistons are A1 and A2, and a small piston of cross section A1 is used to exert a force F1 directly on the liquid. So F1 is applied on the liquid, and the pressure P equals F1 by A is transmitted throughout the liquid to a larger cylinder. This is a larger cylinder of cross-section area A2 attached with a larger piston of area A2, which results in upward force P into A2 as shown in the figure. That is, F1 is applied and it is transmitted through fluid with F2 is equal to P into A2. Therefore, the piston is capable of supporting a large force, that is, large weight of say a car or a truck placed on the platform. This we have seen in many of the garages. Therefore, F2 is equal to P into A2, that is equal to F1 into A2 by A1. By making A2 by A1 larger, heavy loads can be lifted by applying small force. The factor A2 by A1 in the above equation is called the mechanical advantage of the device, that is mechanical advantage of the hydraulic lift. Let us solve two worked examples on application of Pascal's law and hydraulic machines. Example number 5. Two syringes of different cross sections, that is without needles, filled with water are connected with a tightly fitted rubber tube which is also filled with water. Diameters of the smaller piston and larger pistons are given as 1 centimeter and 3 centimeters respectively. There are two parts in the question. Part A is find the force exerted on the larger piston when a force of 10 newtons is applied to the smaller piston. Part B is if the smaller piston is pushed through 6 centimeters, how much does the larger piston move out? Let us answer it. The atmospheric pressure, which is common to both pistons, has been ignored in this problem. Part A. Since pressure is transmitted undiminished throughout the fluid, we know F2 by A2 is equal to F1 by A1, or F2 is equal to A2 by A1 into F1. Therefore, substituting the values of A2, A1 and F1, which is given in the question, we get A2 is equal to pi into pi r square, that is pi into 3 by 2. 3 is the diameter, 3 by 2 is the radius. Therefore, 3 by 2 into 10 to the power of minus 2 meters whole square. This minus 2 is a multiplier for converting centimeters into meters, divided by pi into 1 centimeter, which is the diameter, divided by half, that is radius is 1 by 2 into 10 to the power of minus 2 meters, that is centimeters converted into meters, whole square into 10 to the power of 10 newtons. Simplifying, we get the value as 90 newtons. This is the answer for part A. Next we will take up part B. Water is considered to be perfectly incompressible. Volume covered by the movement of smaller piston inwards is equal to the volume moved out due to larger piston. Therefore, L1A1 is equal to L2A2. Or we can write it as L2 is equal to A1 by A2 into L1. Substituting the values of A1, A2 and L1, we get the equation is A1 is pi into 1 by 2, that is A1 is diameter is 1 centimeter divided by 2 is radius, 1 by 2 is the radius into 10 to the power of minus 2 meters whole square divided by pi into the A2 diameter is 3 centimeters, radius is 3 by 2 centimeters into 10 to the power of minus 2 meters whole square into length is 6 centimeters, that is 6 into 10 to the power of minus 2 meters. Simplifying, we get the value as L2 is equal to 0.67 into 10 to the power of minus 2 meters. That is equal to 0.67 meters. Next question. Question number 6. In a car lift, compressed air exerts a force F1 on the smaller piston having radius of 5 centimeters. This pressure is transmitted to second piston of radius 15 centimeters, that is figure shown below. If the mass of the car to be lifted is 1350 kg, calculate force F1. What is the pressure necessary to accomplish this task? So we have to find the value of pressure necessary to lift this car. Let us assume it is given that G is equal to 9.8 meters per second square. Let us solve it. The figure shown on the screen is the schematic diagram illustrating the principle behind the hydraulic lift, a device used to lift the heavy loads. Now we know F1 by A1 is equal to F2 by A2. Substituting the values of A1 as pi into 5 into 10 to the power of minus 2 meter whole square. So this is 5 centimeters converted into meter divided by A2. Value of A2 is pi into 15 into 10 to the power of minus 2 meter whole square into F2 is given as 1350 kg. Kg should be converted into weight. Therefore, it is 13 mg. Mass is 135 kg into value of gravitational acceleration is 9.8 meters per second square. Simplifying, we get the value as 1470 newtons. that can be written as 1.5 into 10 to the power of 3 newtons. The air pressure that will produce this force is given by the relation P is equal to F1 by EA1. That is 1.5 into 10 to the power of 3 newtons. That is we have calculated previously, divided by A1 is pi into 5 into 10 to the power of minus meters whole square. That is area is meter square. Simplifying, we get the value of pressure P equals 1.9 into 10 to the power of 5 pascals. This PA is Pascal. That is the answer. This is almost double the atmospheric pressure. Next we will take up Archimedes principle. Archimedes, who lived between 287 to 212 BC, was a Greek philosopher, mathematician, scientist and engineer. He invented the catapult and devised a system of pulleys and levers to handle heavy loads. The Archimedes principle states that a body immersed in a fluid, either wholly or partially, experiences an upward force equal to the weight of the fluid. This force is called upthrust or buoyant force, and the phenomena is called buoyancy. That means when a body is immersed in a fluid, it experiences an upward force equal to the weight of the displaced fluid. This is the statement of Archimedes principle. Therefore, this buoyant force represented by F subscripts B is equal to F2 minus F1, where F1 and F2 are hydrostatic forces. FB can be written as FB is equal to VI into rho L into G, where VI is the volume of the solid immersed. That is, the volume of the immersed solid is VI, and rho L is the density of fluid, and G is the acceleration due to gravity. Now we will study about laws of flotation. For a body to float, the force of buoyancy must be equal to the weight of the fluid displaced. This is the law. Please see the figure on the right hand side. Here are three different solids, aluminium, cork and wood are shown in the container. Generally, for example, the liquid can be water, immersed in water. Therefore, here using the equation, previous equation, Vi into rho L into G is equal to Fb, force, buoyant force, that is equal to mg, that is mass into acceleration due to gravity. Therefore, this is Vi rho L G is equal to Vs Ps equal into G, where Vs is the volume of the solid and rho s is the density of the solid. The right hand side is without immersion, left hand side is the with after immersion. Three cases arise. Here rho L, the displaced liquid, the density of the liquid is less than the density of the solid. So in this case, if the density of liquid is less than the density of solid, then the volume of the immersed fluid will be greater than the volume of the solid. That is, in the case 1, in the case of aluminium, the body, solid body, will sink, as shown in the first figure. In the next case, case B, the density of the liquid is greater than the density of solid. That is, rho L is greater than rho S. Therefore, to equate this equation, VI will be equal to VI will be less than Vs. Hence, the body will float partially. That is a cork as shown in the figure. Partially it will be floating. In case number 3, when rho L is equal to and that is density of liquid is equal to density of the solid, as in the case of wood, Vi is equal to Vs. The solid body floats just inside the liquid. Example, wood, as shown in case C, that is the third figure on the right hand side. Hence, if the density of the immersed object is more than that of fluid, case 1, the object will sink, as the weight of the body is more than the upward thrust. If the density of the object is less than that of the fluid, then it floats in the fluid partially submerged. For totally immersed objects, the volume of fluid displaced by the object is equal to its own volume. This is in the case 3. To calculate the volume of the submerged body, let the volume of the object be Vs and a partially be Vp of its submerged in the fluid. Then the upward force, which is the weight of the displaced fluid, is P rho F G into Vp, which must be equal to the weight of the body. Therefore, rho S into G into Vs is equal to rho F floating body into G into Vp. Therefore, G and G gets cancelled. Therefore, rho S by rho F will be equal to Vp by Vs. Therefore, the apparent weight of floating body is 0. This principle can be summarized as the loss of weight of a body submerged partially or fully in a fluid is equal to the weight of fluid displaced. Streamline flow. Hitherto, we have studied fluids at rest. In streamline flow, we study a fluids in motion. That is, this branch is also called fluid dynamics. When a water tap is turned on slowly, the water flow is smooth initially, but loses its smoothness when the speed of outflow is increased. In studying the motion of fluids, we focus our attention on what is happening to various fluid particles at a particular point in space at a particular time. The path taken by fluid particle under a steady flow is a streamline flow. So this curve shown in the figure is the path taken by fluid particle under steady flow. This streamline flow is defined as a curve, the curve shown in the figure, whose tangent is the direction of fluid of the velocity. Hence, tangents show is the direction of the fluid velocity. Please note direction of the fluid velocity at that point, that is point A, point B and point C as shown in the figure. V1, V2 and V3 are tangents at these points respectively. Now we will take a equation of continuity. The volume of an incompressible fluid passing at any point every second in a pipe of non-uniform cross section is the same in the steady flow. Please see the figure on the right hand side. Here in this figure, a typical region of streamline flow is shown with direction of arrows. Here P, Q and R are different regions of the direction of fluid flow. Example, at 3 points P, R and Q in the figure, the plane pieces are so chosen that the boundaries are determined by the same streamlines. This means the number of fluid particles crossing the surface, so as indicated at P, R and Q is same. If the area of cross section of these points are AP, AR and AQ, the speeds of the fluid particles are Vp. This is Vp is the speed at point P, Vr is the speed at point R and Vq is the speed at point Q. Then the mass of the fluid delta mp, that is which crosses AP in a small interval delta t, is given by the relation rho p into AP into Vp into delta t. Similarly, the case for delta mq and delta mr. Thus, the mass of liquid flowing out equals the mass of flowing in, holds good in all the cases. Therefore, these can be equated. That is, rho p into AP into Vp into delta t, that is the mass, is equal to rho q into AQ into Vq into delta t equals rho r into AR into VR. Let it be equation 1. For the flow of incompressible fluids, rho p is equal to rho q is equal to rho r, because density of the incompressible fluid is same. Hence equating, we get AP into Vp is equal to AQ into Vq equals AR into VR. Let it be equation 2. This equation is called equation of continuity, and it is a statement of conservation of mass in flow of incompressible fluids. In general, A into V is constant. Let it be equation 3. A into V gives the volume. Therefore, area into velocity gives the volume flux, or the flow rate remains constant throughout the pipe of the flow. That is, AV is equal to constant, proves that the flow rate remains constant throughout the pipe of flow. Thus, at narrower point portions where the streamlines are closely placed, velocity increases, and it's vice versa. Next, we will study about the types of flows, streamline flows. There are two more types of flows. Some streamlines of fluid flow are shown in the diagram. Laminar flow. If the liquid is flowing in a horizontal surface with a steady flow and moves in the form of layers of different velocities which do not mix, please underline, do not mix with each other, then the flow of liquid is a laminar flow. So, the velocity of liquid flow is always less than the critical velocity of the liquid. Turbulent flow. When a liquid moves with a velocity greater than its critical velocity, the motion of particles of liquid becomes disordered or irregular, as shown in the figure. Such a flow is called turbulent flow. Critical velocity. We have mentioned the term critical velocity. The critical velocity is that velocity of a liquid flow up to which its flow is streamlined and above which its flow becomes turbulent. That is, up to the critical velocity it is laminar flow, and after above that it is turbulent flow. With this, we come to the conclusion of part 1 of chapter number 10 on mechanical properties of fluids. In the next part, that is part 2, we will study about Bernoulli's theorem, viscosity and surface tension. Till then, goodbye.